Hey everyone, welcome to the very first episode of Calculuscious Explains It All, where I, Calculuscious, aka Mathy Cathy, explain not quite at all, but whatever I choose to talk about in a way that hopefully makes sense, despite my rambling and awkwardness. You've been warned. For this very first episode, I have chosen to explain limits. Now, I chose to explain limits not only because they are the first unit of study in a beginning calculus class, but also because I don't think that they get the recognition they deserve for how powerful and amazing they are mathematically. The other major topics that you're going to study in beginning calculus class will be defined by a limit. And so I think it's really important that you get to know them, not only how to evaluate them, but hopefully from this video you'll get a little bit of what they are conceptually. Before we jump into some specifics, I just want to tell you a little bit about myself. Ever since I can remember, I have loved math. There I am. My first year in college with my math major buddies, and look at what we're doing. We're in our dorm room taking a picture of ourselves with a calculus book. So that's how much we loved calculus. And even though I really loved math, there was always this part of me that, like there was this voice in the back of my head saying, but you don't know it as well as you should. I was never confident in math. Sometimes I would open up my textbook. This is a picture of the inside of my calculus textbook, limits, the limit chapter. And sometimes I would open it and I would just say, I don't understand this. Like, I can tell you how to do a limit. I can evaluate a limit. I can say all of the different methods and when I should use what method. But what am I finding really? Sometimes I just didn't quite understand that. And so I really hope in this series, I can explain some basics, but also I can explain the concept behind what you're doing. Maybe in a fun way. I don't know. We'll see. Okay, so if you are just starting out with learning what a limit is, this formal definition is not going to be very helpful. I put it here because I think it's important to recognize that it's out there. And for those of you who are gifted mathematically, you might look at this and say, it's really no big deal. And it's not. However, for the common folk like us, when we're first starting out, something like this looks really scary. And so I put this slide here just to tell you that this is here. At some point you'll want to know it. But again, if you're just starting out, ignore it. Try to first understand conceptually what a limit is, like the big ideas behind limits. And then I suggest maybe coming back to this formal definition. There's also like a graphical component to this that you could look at that may be helpful, and I think it'll click. But again, I don't think this is a good place to start, even though some hardcore calculus classes would start here. That's not me. Okay, this is more me. What is a limit? It is a sneaky boy. It is a sneaky mathematical thing that allows us to do things in math that we typically can't do. Okay, for example, take a look at this graph of this, piecewise function. If I said, find the function value at x equals 0, let me grab a pen. Boop. X equals 0. There's a hole there. So you would say that x equals 0, f of 0, the function value at x equals 0 is undefined. It doesn't exist. Okay, and that'd be right. However, what a limit does is it sneaks in and it says, I could tell you what that is. That's 2. All right, so that's like my very simple way of explaining to you what a limit is. And what I want to do for the rest of this video is give you some resources, some examples, and then some slides at the end where I show you where we can go with limits to hopefully get a nice rounded picture of what a limit is. Okay, so here's a resource. Steve Strogatz is one of my favorite mathematicians. He writes some amazing pieces. He writes essays, he writes books, he writes professional articles about math. And he always has a really nice approach to how he explains things so that everybody can access the content and understand it. And so in this article, I'm not going to read all of this, but you may be able to see toward the bottom that one of the things he uses to talk about a limit is this scenario where, I don't know, let's say you're like 10 feet away from a wall and you walk halfway to the wall, so that would be 5 feet. And then you walk again halfway to the wall, so that would be 2.5 feet. And you keep doing that. The question is, how many steps will it take you to get to the wall? And what he says is, to reach the wall, you would need to take an infinite number of steps. Okay, yeah, that can't actually be done, right? But that's sort of the idea behind a limit. You can't actually do something mathematically, but a limit says, yeah, let's try it anyway and see, what happens. Also, just because I want to practice saying this word, okay, not only would you have to take an infinite amount of steps, but by the end, those steps would become infinitesimally small. Yay, I said it. Okay. I recommend reading this article, and if you're a part of my Google Classroom, I have it in there because it's a really good read. It's a quick read, and I think it sort of sets you up to understand limits in a good way. Okay, moving on. Here's what I would like to discuss in my examples today. Actually, not all of these. I showed you all of the methods for evaluating a limit. We'll talk about substitution first. We'll talk about some approximation methods, numerical and graphical approximation. We'll touch on manipulation. That's probably it. But I'm going to show you some examples where we use some of these just so you can get the hang of how to evaluate a limit, or at least the beginning of how to evaluate a limit. But as I talk about them again, I'm going to always go back to, I want you to understand the concept of what you're finding when you find a limit, when you evaluate it. Okay, so let's start with something very simple. And this is where I go away because I have to use this thing to write, and I'm super awkward at it still. And I also apologize in advance for my writing. I don't know, we'll see how this goes. Okay, so let's start with a really simple example, and this is where I should tell you that the first thing you should always try when evaluating a limit is substitution. So take a look at this math that you're seeing. What we would say here is the limit as x approaches 5 of x squared plus 3. Okay, or you could say it as the limit of x squared plus 3 as x approaches 5, but I feel like that's awkward. So basically what you're looking at here with this type of limit, and this is where you always start, is you're looking at the function. Let me grab a pen, and I gotta make it a little bit thinner. Okay, what you're starting with here is a function. F of x equals x squared plus 3. And you're saying, okay, let's look at this function around x equals 5. That's what a limit is asking you to do. But, in this case, and this is what, again, you should always try first is, can you just sub in 5 to that function? So, am I breaking any math rules here by taking 5 squared and then adding 3? No, I can do that, right? 5 squared plus 3, that's equal to 28. So therefore, the function value at x equals 5, or in other words, the y-coordinate when x equals 5 on this parabola is 28. And therefore, that's the answer to your limit. So two things I want you to get out of this example are, one, the first thing you should always try is just subbing in the value and seeing what happens. And two, a limit like this is just finding a function value. You're just finding the y coordinate when x equals whatever is right here. Okay, I have this little Mimi guide down here saying why though, because if you have a limit this simple, it didn't need to be set up as a limit. It's just the same as the function value. So it is the same as f of 5. All right, so let's move on to a second example now where we look at something that is going to be a little bit trickier. The limit as x approaches 5 of x squared minus 25 over x minus 5. Now I want you to keep in mind again that I said the first thing you should always try is substitution, even if you know it's not going to work. You might be thinking to yourself, well, I know when I take 5 minus 5 in the denominator, I'm going to get 0, and I can't have 0 in the denominator. However, I still want you to, I tell my students this, I want to see you talking it out or writing it out because it's important. I'll tell you why when we do it. 5 squared is 25, and 25 minus 25 means we also have a 0 in the numerator. Okay, why that's important is because 0 over 0 is not considered undefined. We say that when we divide by 0, when we take any real number divided by 0, it's undefined, except when you take 0 divided by 0. 0 divided by 0 is what we call, okay, I'm going to type this because I'm not going to be good at writing all of that out. This is what we call an indeterminate form. Let's make that blue. Okay, never mind, maybe not. Indeterminate means, okay, this is not the most formal definition, but here's what I say. Indeterminate means that you have to keep going and try to find another way to get your answer. Indeterminate is not the same as undefined. I like to say that whatever method you used did not determine the answer, so try something else. And so what I want to try next with you, I want to show this to you, is I want to show you a numerical approximation of this limit. So I can't sub 5 in for the x's because I get 0 over 0 and that's not working out for me. But actually what a limit's doing is it's saying, let's see what's happening as we get as close to 5 as we can. Okay, we can't get to 5, but you know, we could try some number really close to 5, like x equals 4.99, something like that. I'm going to write that over here actually. So, by the way, before I write this, in my methods for evaluating, I just tried substitution and it did not work. So now I'm moving on to a different method and I'm going to show you numerical approximation. Okay, so again, I can't sub in x equals 5, but how about x equals 4.99? Which I would argue is pretty close to x equals 5. So what I'm going to do here is take 4.99 squared minus 25 divided by 4.99 minus 5. And what I get is 9.99. I'm going to write that over here. Okay, now you shouldn't just use one approximation if you're going to do a numerical approximation method, especially because what we just did was we chose a number that was less than 5 and we got a value, but you know, sometimes it occurs that choosing a value on the other side of your x coordinate, meaning now what I'm going to look at is something greater than 5, you could get a different answer. And that could, you know, determine what you say for your final answer here. So what I'm now doing, you may notice, is I'm choosing a number greater than 5, but very close to 5. and I'm subbing it into my function to see what I get, and take a look at that. I get 10.01. So for this row, I say when x is 5.01, I get 10.01. So what we're looking at here, well, this is our y, is that most likely the answer to this limit is 10. Okay. What I'm going to do now, before I just end this problem and say there's my answer, that is your answer, okay, I just approximated it numerically, is I'm going to go to the graph now of this function, and I'm going to see what's happening there. For that, however, I should have had this set up ahead of time. Sorry. I'm going to go to Desmos and graph the function. Okay, I don't know if this is surprising to you or not, but when you graph this function, you get a line. We'll talk about that in a moment. All right, in particular, we're looking at when x equals 5, and the thing about this line is it looks like it has a function value there, right? It looks like the y-coordinate is 10, and that's what we predicted with our numerical approximation. However, if you actually hover with your cursor over x equals 5, you will see that it is undefined. So if you were to sketch this for yourself, you would sketch a line with a hole at the point 5 comma, it is 5 comma 10, okay, but here's, another take on what is a limit. Like I said, it's a sneaky boy. So if we sketch, oh, that's so bad. If we sketch this line, okay, I want to specifically show you that you should be putting a you should be putting a hole there. Okay, I'm back. Look at that. I took a moment because I was getting nervous, and I sort of wrote it all out for you here. Okay, so this is like what you could show as a graphical approximation of this limit answer. Here's the function f of x equals x squared minus 25 divided by x minus 5. And what I want you to see here is that f of 5 is undefined. There is a hole there. There is no y-coordinate that is associated with x equals 5. However, this sneaky limit boy comes in and says, but where are you on the y-axis? You're at 10. Okay. So this is a really good problem that we're looking at right now, because I like to show that substitution gives you that indeterminate form of 0 over 0. I like to show you that you can easily use a numerical approximation to find that what you are actually close to, however, when x is close to 5, is 10. And I like to show you that graphically you can see that ordered pair would be 5 comma 10, however, there's a hole there. Finally, I want to show you one more thing. We just sort of beat this example to death, and that is manipulation. I want to show you how you can actually not only approximate this answer, but get the exact answer of 10 using just some simple algebra. So if we have the limit as x approaches 5 of this function, we could rewrite that function in different forms to try to evaluate the limit with substitution. And so what I mean is the numerator could be factored. And then when we factor the numerator, we can see that we have common factors that could be divided out to 1. So x minus 5 over x minus 5 cancels, or whatever you want to say, divides to 1. And so, therefore, what we could use to find the answer to our limit is just the x plus 5 that's left. Using substitution at this point, meaning take this number and fill it in for the x, we see that we get that answer that we were approximating of 10. Okay, and this is one of the big things that students get hung up on with limits is all of the different manipulation techniques that you can use to actually find the exact answer to a limit. And I really think that sometimes the concept of a limit gets lost in all of those different things that you might have to try algebraically or eventually trigonometrically to find an answer to a limit. So what I want you to keep in mind as you keep going is a limit is just trying to find what, I want to try to sub this in. How do I do that? How can I do that? Where would I be if I could do that? That's what we're doing with a limit. All right, something important to mention before we move on, and I should have had my limit that I want to refer to here written, but I didn't. Oh wait, yes I do, there it is. Okay, the limit is not the same, finding a limit is not the same as finding a function value. So for this graphical example where we have the graph of y equals g of x, if I ask you to find the limit as x approaches -2 of g of x, it is not going to be the same answer as the function value at -2. So g of -2, that's saying what's the function value when x is -2, that's the corresponding y coordinate, and you would be looking for the closed point to answer that. And so we would say that g of -2 is 3. However, a limit never concerns themselves, limits never concern themselves with random points out in space. That's how I describe it. So what you would do to find the limit as x approaches -2 of g of x is you would say, okay, this graph, where's it going? From the left. Okay, we like to talk about approaching a limit from both sides of the x coordinate. So from the left, as I approach x equals -2, okay, where's that hole? That's what it's asking for. It's at 0. And it happens to be the same as you approach from the right. That hole, okay, where the graph would be going is a y-coordinate of 0. And therefore, that is the answer to the limit as x approaches -2 of g of x. It's like, where would I be if I could go there? If I could just continue with this graph, what would that y-coordinate have been? It would have been 0. Keep in mind that this is something that we're going to talk about a little bit more, approaching a value from the left and the right to find a limit answer as we move on to a couple other examples here. Take a look at this one. Okay, do you remember the first thing that I told you should try when evaluating a limit? Yes, you do, of course. It's direct substitution. Okay, so I'm going to take this 3 and sub it in where I see the x's. And I always think that's important because that tells you what you should be thinking about next. In this case, you have a 3 in the numerator and you have a 0 in the denominator. Now remember, 2 examples ago, I said if you have 0 over 0, that's called indeterminate, and we could go through all of these other methods, or one of these other methods, to find the answer. In this example, you don't have an indeterminate form. You have 3 over 0. 3 over 0 is undefined. And depending on what you're trying to do, that could be good enough to just say that this is undefined. However, okay, going back to the fact that a limit is a sneaky boy. A limit is going to sneak in here, and you could do more with this. You could say, but let's take a look at it deeper, and what is it actually doing? Okay, an undefined answer means something in particular. And I think that the best way to see what's happening here is to take a look at the graph. Okay, there's all sorts of ways that you can approach this. But just in the interest of time, I think that approaching it graphically would be good. This time I'm just going to go to the graphing calculator. And, I don't want a 3, I want an x. I'm just going to take a look at this function on my calculator here. There we go. Okay, and if you took a pre-calculus course, I would hope that you would recognize what's happening right here at x equals 3 is there's a vertical asymptote. All right, so I paused for a moment just to draw this out to show you the vertical asymptote here. So yeah, we're not wrong in saying that, 3 divided by 0 is undefined. However, something more that we could say about this limit, if you take a look at what's happening as the graph gets closer and closer to x equals 3 from the left and gets closer and closer to x equals 3 from the right, is the graph just sort of shoots up around that vertical asymptote. And what's happening there, and this is something that's characteristic of vertical asymptotes, is that you could say that this limit, in particular this one because it's shooting up on both sides from the left and the right into unbounded positive y coordinates, is that what you have here is infinity. Okay, around a vertical asymptote, a limit will always be infinity or negative infinity. Now, infinity is not a real number, so that's why, once again, I'm saying that our, this is so badly written, sorry. Our answer of undefined is not wrong. However, looking at it a little bit deeper, a limit can sneak in and say, but let's call that infinity, and that tells you a little bit more about it. It says that there's a vertical asymptote. All right, here's another one that we're going to take a look at graphically and numerically after we do substitution. So for this one, we're doing the limit as x approaches 0 of the absolute value of x over x. Let's sub in 0. The absolute value of 0 over 0 is indeterminate. And so we should do a little bit more with this one. But what you are going to see, and this is a common misconception that students have, is that whenever you have an indeterminate form, there is always an answer to the limit. I want to say yeah, kind of, but no on that, okay? So let's talk about what this means first of all. If you take the absolute value of any number divided by itself, if you just think about that, I hope you would realize that what you're going to get out of that is one of two values. You're either going to get x equals 1, right? Like, let's say we can't throw in 0, but we can throw in, like, 2. The absolute value of 2 divided by 2 is 1. Let's throw in 7. The absolute value of 7 divided by 7 is 1. Or what's the other value you could possibly get out of that? Do you see that it could be negative 1? If you throw in a negative number, like negative 3, the absolute value of negative 3 is 3, and then divide by a negative 3, and that is negative 1. And so what you're seeing for this function is it has two possible values, and 0 is sort of where it splits into, or it splits, the graph into those two possible values. So I'm rambling, so let me just show you what I mean graphically. All right, so let's take a look at the absolute value of x divided by x. And actually first, before we take a look at the graph, I just want to show you the table. And what you can see is that all of the numbers less than 0 are negative 1, which should make sense, I hope. At 0, we have an error, which should make sense. Can't divide by 0. 0 over 0 is indeterminate. And to the right of 0, or numbers that are greater than x equals 0, you have a y coordinate of 1. Okay, graphically, here's what you see. Okay, so I took a moment and I paused and I drew that out, but what I wanted to show you in particular is if you sketch the graph, what you should be doing at the 2 points where you need to plot for x equals 0, you should have holes there because there is no function value for x equals 0. All right, and this is one where I want to talk a little bit deeper about approaching from the left or from one side and then approaching from the other side. So what you should do to answer this limit is you should take the limit as x approaches 0 from the left. And the way that we show we're approaching from the left is we put this little minus sign here. And again, I'm just going to call this f of x. Let's say that we have f of x equals the absolute value of x over x. All right. And what I'm seeing from the graph and from the table was that I'm getting -1. Then you also want to show what we call a right-hand limit. You want to say I'm going to approach 0 from the right. And what we do for that is we put a little plus sign on our x value. And what we saw from the graph and the table is that we get +1. And so what's happening here is that if you come from one side of x equals 0, you're getting one value, and you come from the other side of x equals 0, you're getting a completely different value. And this is an example of a limit that, this is very exciting, does not exist. Yep, doesn't exist. Isn't that exciting? Isn't that fun? Okay, so we got this indeterminate form, and from that indeterminate form, we could say, okay, we can calculate a left-hand limit, or okay, we could calculate a right-hand limit, but something that's extremely important to know about limits is that they have to be approaching the same value from the left and the right to exist. Since this is an example where that does not happen, what we are going to say about the limit as x approaches 0 of f of x again, is that it does not exist. Okay, so I like to think of limits, as I said before, as sneaky boys. You know, they're going to pop in and say, oh, you're not allowed to divide by 0? Well, let me try to help you there. And sometimes it works, and you're able to calculate a value that you can't always calculate, like this one. Okay, this limit answer was 10. However, limits, okay, listen to this, limits do have limitations to them. They can't always exist, and this is an example where they don't exist. The left and the right-hand limit must match for the overall limit to exist. All right. So those, I hope, are some helpful examples of some different ways that you should look at limits, at least initial examples. I encourage you to keep going with that process. And what I want to do now, here I'll come back to you, is I want to talk about where we could go with limits. Like, so what? A limit will find a function value that's not really there. Okay, that's great, but how does that help us at all? So here's what you're going to see as you continue your study of calculus. Let's say we have a curve, and let's pick one particular point on that curve, and let's draw a tangent line to that curve. Oh my gosh, I'm so proud of myself for doing this on camera. Okay, so you're looking at a line. That line definitely exists, right? And there's definitely slope. That line has slope. The question is, how do you find that slope? And the issue is that you only have one point to find that slope with. And if you remember, you need 2 points to find the slope of a line, right? Hopefully this looks familiar. You don't have 2 points though. You have a curve, you have one definite point that you know you drew through that curve because you drew a tangent line, and a tangent line only hits a curve at one point. So what are you going to do? Well, I'm not going to go over all of the mechanics of it right now, but I'm going to tell you that a limit is what gets you there. A limit will find the slope of a line if you only have 1 point on that line. And eventually we would call that a slope of a curve. And eventually you call that something very important in calculus, which is called a derivative. Okay? You know, why is that helpful? Well, in physics, a slope is a rate of change. And if you want to find an instantaneous rate, for this example, assume that a watermelon dropped from a tall building falls y equals 16 t squared feet in t seconds. Find the watermelon speed at the instant t equals 6 seconds. Okay, that's a rate at just 1 point, or in other words, a slope at 1 point. And what you're going to be able to do to answer that question is set up a slope between 2 points and then use a limit to turn it into 1 point. Okay, and it's a pretty powerful idea. It's really important to your initial study of calculus. And I put this little note here. If you're on my Google Classroom, you can see this is in something called Intro to Rates of Change, and it'll explain that process to you. Okay, so that's just one place that a limit's going to take you. That's actually a really important place that you're going to go with it. Later on, you could start to talk about area, okay? And let's start with something really basic, the area of a circle. How do we prove that the area formula for a circle is pi r squared? Well, going back to Steve Strogatz, my hero, one of my heroes for a minute, in his article, Take It to the Limit, he talks about this process of cutting a circle into sectors and then rearranging those sectors to form a shape. And if you could imagine taking an infinite number of sectors, which would really be applying a limit. It'd be applying the limit as the amount of sectors goes to infinity, then you could see that that shape that you're rearranging those sectors into is a rectangle. And so you can sort of see from this nice diagram here that what we have, okay, we have the radius, and then we have pi times the radius, you know, which is basically like half of your circumference here. Half because you have half of it down here and half of it up here. Okay, so you do have to use the circumference formula in this proof. But having those dimensions of your rectangle, once you turn it into an infinite number of pieces, you have a rectangle. It is just as simple as taking this length times this width, and you get pi r squared. Okay, and then you could develop that into something called, develop that idea of slicing into an infinite number of infinitesimally small pieces into, you could talk about that as an integral. Okay, and that's much later in calculus. So what I'm trying to tell you here is that everything else that you're going to study in a first year calculus course, it's going to start by being defined by a limit. And so understanding limits and what they can do is extremely important for the rest of your study. Okay, take a look at that. Steve Strogatz is smiling. I'm smiling. I really hope you're smiling, and I hope you enjoyed this video, and I hope to see you again soon. Bye.